Other is too complicated to explain. So look at the in-plane scheduling. The neutron is hitting the surface at the layer perpendicular. In the scattering is small angle. Then the momentum transfer is practically in the plane. So in the in-plane scheduling, what you're looking at is along the plane of the moment. And if there are holes in the membrane, you want to see the hole. But you can't see it because one of the difficulties of biological system is that all biological molecules are made of carbon, oxygen, nitrogen, and hydrogen. All are similar atomic number. It's very similar to H2O. So there's no contrast between H2O and the lipid molecule. But if you exchange H2O to deuterium oxide, D2O, heavy water, deuterium has a very peculiar property to neutron. So neutron will see the D2O very differently from lipid molecule. And you'll be able to see the contrast if there are holes where the water goes through. And indeed, that's what we saw. That if you change to D2O, there's a peak. And on the other hand, if the lipid molecule is deuterated, then you have to exchange to H2O to provide contrast between hydrogen system and deuterium system. And it's easy to analyze this and to know that the whole antibiotic made in the membrane is about 4.4 nanometer. We can measure this very precisely. But strangely, we have done other experiments, too complicated to explain. There are only about 4 or 7 antibiotics in each hole. That means it's impossible to have this antibiotic line the hole. Yet there are holes. So it's very strange. How is it so? How can antibiotics make a hole without enough antibiotics in the hole? So what I want to do, this has been the question in not only to me, also to the community of this research. How can it make a hole? We take the multi-layer system with hole in there, and we remove the water even more dehydrated, and it will become crystal. Now, why that is the case? Think about this. Membrane is a soft material. So its entropy includes this fluctuation of this plant. Okay? And if you do bring two membranes to each other, you decrease the possibility of fluctuation, huh? Because you interfere with each other. You're decreasing the entropy, increasing the free energy, so they repel. If you try to bring two membranes to each other apart, they repel. Okay? Now think about membrane with a hole. If you bring two membranes to each other parallel and line up the hole, that means there is a maximum interaction between two membranes, right? But if you displace the membrane from each other, so the hole don't line up, you decrease the area of contact a little bit, right? Because now a little bit of membrane is facing the hole. So the repulsion would be a little less, but nevertheless less. Then, if you have the multi-layers, and you dehydrate means you decrease the distance between membrane. You're going to force all this hole into a hexagonal pattern, and also the neighbor would displace a little bit so that they avoid hole alignment. And as a result, it will become ABC hexagonal stacking. And this is exactly diffraction pattern tells you that's what happened. The layer of holes stack up ABC. So now you have diffraction pattern. You can do the electron density construction to see how the hole looked like. That's the purpose, right? But as far as I know, nobody has ever studied diffraction from soft matter. This is, in a way, very strange diffraction pattern. Why? This diffraction pattern is obtained from my laboratory X-ray system. If you take it to synchrotron radiation, where the beam is very sharp, the peak will be so small that you can hardly see it. Sharp peak means you have a good long-range order. Good long-range order means good crystal. Good crystal give you sharp peak and also a lot of diffraction peak. But why here? Very sharp peak, but very small number of diffraction peak. Because in a molecular crystalline, the unit cell is defined by position of atom. It's like delta function, and the position of atoms. But in a soft matter, unit cell, the molecule is continuum, not well-defined position. It's a fluid. Even though it's crystalline the whole, but the unit cell still continuous distribution. Diffraction is Fourier transform of real space distribution. So if you Fourier transform a continuum unit cell, you get a broad Gaussian and damp out. So you're limited to finite range of diffraction peak. So you have small diffraction peak number. That's fine. There's nothing wrong. If you are doing soft matter, that's a bona fide diffraction pattern. But to construct the electron density, you need to solve the phase. I don't know if you have learned this or not. X-ray diffraction measure absolute intensity. But the amplitude is, the diffraction amplitude is the magnitude plus the phase times the phase. It is a phase problem. The phase problem of protein is famous, right? People solve the phase problem of protein, got Nobel Prizes. Many of them. You would think that, hey, if people can solve the phase problem, this must be a very simple problem, right? Firstly, small number of peaks. Secondly, because of the symmetry, the amplitude may be real function. Therefore, there's only either plus or minus. In other words, the angle is either 0 or pi. Only two choices. Well, we find out that actually it's very hard to solve this phase problem because even though there are a lot of tricks for solving this complicated phase problem, The reason you have all those tricks is because the unit cell of proteins is asymmetric. Proteins are always non-centrosymmetric. It's always chiral. So it's asymmetric, therefore there are all kinds of tricks in there. If you apply those tricks to this program, you get mathematical identity. Totally useless. So we struggled with this program for many years. Finally, we also did anomalous diffraction, just like protein crystallography. You introduce an atom into the system and use the X-ray of the wavelengths correspond to the absorption edge. And if you do that, the scattering amplitude consists of two parts. F0 is the scattering amplitude for, or diffraction amplitude of the whole system. F2 is of only anomalous atom with a coefficient of real part and imaginary part of anomalous scattering factor, and Fn is normal scattering factor. If you square this, you have only two terms. And better than this is that actually the real part of amplitude and anomalous scattering amplitude is better than 10 times our imaginary part. So actually this term is negligible, and you can reduce this measured intensity. This is a complex number, but you measure the magnitude in terms of only linear F0 and F2 with the amplitude real part. And therefore, you can use this plot function of lambda prime and use a slope and intercept to obtain both F0 and 2. And in fact, you still have the phase problem, and I cannot, I don't have time to talk about it. But let's say that you have solved the F0 and 2. Okay, one is for the whole system. F2 is only for the anomalous atom, and you will see that in the soft matter diffraction, that F0 is always not good enough. The number of peaks is just not large enough to be able to resolve the structure of the unit cell. It's a mess. However, F2 is very clear. So the trick is use F2 to solve the problem. We use this technique to look at many different antibiotics. And only one of thousands of antibiotics, I told you that this kind of antibiotic, which walk on membrane, human has one, monkey has one, dog has one, frog has one, everyone is slightly different. We studied many of them. Only one make holes in the membrane by lining up the hole. This is what everybody expected. It will line the hole. If you read the older literature, people guess how they make hole. They all draw this cartoon. But this is a wrong cartoon. Only right for one particular antibiotics. All others we find has very small number of antibiotics in the hole, but somehow it forces the lipid bilayer, upper layer and lower layer to merge, like an inside of donut hole. And this, we call this toroidal model. This now is a standard literature, standard terminology in the literature. And actually, this is a very interesting topological question. because there's a topological change from before the pole and after the pole. Okay, so this is actually how the pole looked at made by the antibiotics in the membrane. The question is, why? Why antibiotics make hole like this? And remember, my movie show you that it begins to make pole only when the membrane expands about 4%. This is a very, very important point. Why the membrane expands? Because the antibiotics bind to the membrane, right? It binds to the membrane in interface, or it stretches the membrane area. So 4% means there are some number of antibiotics attached to the membrane in order to stretch the membrane by 4%. This 4% I want to emphasize is very, very important. Imagine if these antibiotics, when they go to the membrane, make it whole without requirement of 4% expansion. That is, every antibiotic will make it whole. Then it will not only kill bacteria, it also kills its host cell, right? It will be a poison. It's totally useless. So this means that we have found that there is a ratio. There's a ratio. Or I would call that the concentration on-off switch. Before it reaches 4%, it's harmless. It doesn't make whole. Once it reaches 4%, it makes whole. You have to understand that's how biology works. People often describe biological systems like machine-like, very precise. Why? How? Because there are a lot of on-off switch. Sometimes it's on, but then when it's needed, it's on. Otherwise, it's on. What is a switch? How can biological system have a switch? It cannot be a mechanical switch. It cannot be an electrical switch. It can only be concentration switch. The only thing a cell controls is the concentration of DNA, of protein, or the compound produced by protein. All switches in biological system are concentration switch. So this antibiotics has a concentration switch. 4% area expansion means something like antibiotic every, say, about 20 lipid molecule, you have to have one antibiotic. A certain concentration produces 4% expansion. Okay? So the question is, how so? What is the physics? To understand that, you really need to know what is bacteria doing in the membrane. We know it's black hole, but actually, when it binds, what happened? What happened in the membrane? So to do that, we sort of invented two methods to look at what's going on inside the cell membrane. And this, as I'm going to emphasize at the end again, is the key for understanding biological system. You have to be able to observe, to detect what's going on. We have one method called oriented circular dichroism. Circular dichroism means absorption difference between right-handed polarized light and left-handed polarized light. Most physicists and chemists don't care about this because most molecules are symmetric. Unless you are prime magnetic field or something. You don't have circular dichroism. But biochemistry, everybody is circular dichroism because all molecules in biology are chiral. Right-handed, left-handed helix, so on and so forth. They're not symmetric, not mirror symmetry. We thought, so this is a very common spectrum, but usually you put in solution and measure this average circular dichroism without any orientation dependence. We thought that circular dichroism had to have orientation dependence. We have to be able to say helix is in the membrane is parallel to the membrane or perpendicular to the membrane. And so we prove that that is true, and this is the method we developed to measure whether antibiotic is parallel to the membrane or perpendicular to the membrane. We also use X-ray diffraction to measure the membrane thickness. Remember that antibiotics make membrane area expand because they touch this interface, expand the interface, area increase. Then the chain in between, this is barrier, has to be stretched, must become thinner. The thickness of the thinning and area is complementary, of course. But thickness, you can use X-ray to measure to 0.1% Armstrong thickness change. Very precise. Area change, very difficult to be precise. Maybe 0.1% or something. Very difficult to be precise. So we use X-ray to measure. And when we did that, we found a very interesting thing. When the antibiotic come to the membrane surface, they're all parallel. As you expected, it's a helix with one side hydrophobic, one side phosphoryl. You will be expect to be parallel to. And in the meantime, because it's an interface, stretch area, therefore membrane becomes thinner. And you see that thinning is in proportion to the amount attached to it. Totally expected. But above certain concentration, the thickness stops. And the helix began to turn from parallel to perpendicular. So with this input, now we can go ask, why do they make holes? Why they just switch from no hole to hole at certain concentration? So let's discuss the physics of making hole. If you have a thin layer, you make a hole. What is the physics? What is the energy? First, you have a line tension, because you open a line, there is a positive energy, and that will be proportional to circumference, proportional to R. But if you have a tension try to decrease area, right? It always tries to decrease it. So you favor making a hole, because that would area or layer becomes smaller. Hole is empty. And that term is R squared. Area is R squared, is negative. You combine these two terms, you get a maximum, curve of maximum. In other words, if the hole is very small, you shrink back. No hole is stable. But if the hole is bigger than some gamma divided by sigma, then you expand indefinitely. So it's impossible to have a stable hole, right? So how come antibiotics always make stable hole in the membrane? The reason is this. Remember that sigma tension is area per unit area. When the antibodies come to the membrane, it's straight interface, straight to membrane, it's energy. So you have an energy proportional to the number of peptide on the surface, P. L is a ratio of antibiotics. We call that peptide because antibiotics is peptide. P over L, number of lipids. It's just a normalization. But when you make a hole, we found that these antibiotics would go to the hole and become perpendicular. And that relaxes the number of peptides on the surface, make the tension a little less. So you have this minus total number of peptides minus number on the circumference in the hole. But this number of peptide go to the hole is proportional to the circumference. Right? So you bring this back to here with a radius R and bring this to here. You create a cubic term. And this cubic term is positive. So it turns the curve around. And it's a classic Landau free energy for first order phase transition. So these antibiotics work by a phase transition. At concentration on the membrane less than some critical number, no hole is stable. This is stable. But if it's above this critical concentration, the hole is stable. So there is a phase transition by concentration. This is very, very important. Otherwise, it won't work. If you have antibiotics in a solution, you bring bacteria into the solution, you bring human cell into the solution, what happened? These antibiotics, I told you, is a small protein, are mostly positively charged. And bacteria membrane surface is negatively surface charged. It's by nature. Every bacteria surface is negatively charged. Human cell membrane is neutral. So these antibiotics are mostly attracted to bacteria. And if the solution concentration is right, and we must have done it right, and our system is doing it right, the concentration is so that the amount attracted to bacteria would exceed the critical concentration. And amount, they will go to the human cell as well. Antibiotics doesn't know which cell is what. It just go by physics, right? You go to negative charge because it's positive charge. And don't go to neutral surface that much. So it's safe. The neutral cell membrane is safe, but it always go to bacteria with enough to kill it all. So that's how it works. So with this understanding, we can now go back to the real cell. The reason that real cell is very difficult to study is because they are alive. And there are a lot of reaction because they are alive to what happened on the membrane. So we have to do a lot of experiment. And it will take another hour to explain why it works that way, which I'm not going to do, of course. So that's basically the story of how the antibiotics works. Even though we understand the bacteria now, this has not been approved. People still try to apply for approval for this new kind of antibiotics. However, recently we found that there is even